Welcome back. In this video, we're going to look at example problems of integrating by partial fractions. Let's get to it. All right, so here's our first example. We have the integral of 4 divided by x cubed minus x. Now, a common theme for all the integrals we're going to look at in this video is that in their current state, we would not be able to solve them. In order to solve the integral, we have to break up the rational function into partial fractions. And the reason we do that is because those partial fractions will then be functions that we are able to integrate. And so the first step to solving an integral with partial fractions is to fully factor the denominator of your integral. And so let's do that. I see in our denominator here that each of these terms have a common factor of x. And so if we pull that out, this will be equal to the integral of 4 divided by x times x squared minus 1. And that is multiplied by dx. Okay, and now what we're left with in the denominator is x times x squared minus 1. Now this isn't fully factored yet because x squared minus 1 is a difference of squares. And so we can factor a difference of squares. In this case, x squared minus 1 will become x plus 1 times x minus 1. And so this will be equal to the integral of 4 divided by x times x plus 1 times x minus 1 times dx. Okay, so now we have fully factored the denominator of our rational function, and we can now see that we have 3 distinct linear factors. And what I mean by a linear factor is a factor where x is to the first power. Okay, and so we're going to do a little side work here. Now that we have fully factored the denominator, we can start working on breaking it up into partial fractions. So we're going to take a break from the integral for a second, and we're just going to work with that rational function. So we have 4 divided by x times x plus 1 times x minus 1. And this is going to be equal to 3 different partial fractions. We're going to have one partial fraction for each of these linear factors, right? So one of them will have a denominator of x. Then we're going to add that to another fraction with a denominator of x plus 1. And then we're going to add that to another fraction with a denominator of x minus 1. Those are the 3 factors from our denominator. And now the numerators, those are going to be constants that we want to solve for. And we will represent those with letters. So we'll have A, B, and C. And so what we want to do is solve for the values of A, B, and C, and then we will be able to rewrite this rational function in our integral with these 3 simpler rational functions that we will then be able to integrate. And so the way we go about solving for A, B, and C is we get a common denominator between the 3 fractions, which will be this denominator right here, and then we will be able to set the numerators of our 2 fractions equal to each other. And so in order to do that, we need to multiply each of these fractions by a form of 1 for each of these linear factors that the fraction doesn't have in the denominator. And so for example, what I mean by that is if we look at this first fraction here, a divided by x, in order for this to have a common denominator between these 3 fractions, which is going to be this denominator right here, we would need to multiply this fraction by a form of 1 for each of the factors that it does not have in the denominator. So that would be x plus 1 and x minus 1. So what we would have here for that first fraction is a times x plus 1 times x minus 1, and then the denominator would be x times x plus 1 times x minus 1. If we did that for our second fraction, we have x plus 1 in the denominator, but we need x and x minus 1. So we would have plus b times x minus 1 times x divided by x times x plus 1 times x minus 1. And then we would do the same thing for our last fraction, which in order to get that common denominator, it would need a factor of x and x plus 1. So we would have plus c times x plus 1 times x divided by that same denominator of x times x plus 1 times x minus 1. And this is all still equal to this rational function right here. So we have 4 divided by x times x plus 1 times x minus 1. Okay, and by doing that, we can now combine the numerators of these fractions since they all have the same denominator. And so if I just rewrite this to reflect that, we will have these 3 terms added together divided by that common denominator of x times x plus 1 times x minus 1. And now, since both rational functions on either side of this equation have the same denominator, and we know they must be equal, we can set the numerators equal to each other, and then we will be able to solve for a, b, and c. Okay, so we'll have 4 is equal to a times x plus 1 times x minus 1 plus b times x minus 1 times x plus c times x plus 1 times x. So now we have an equation that we can use to solve for a, b, and c. This was the long way of doing it. From here on out, with the rest of our examples, we're going to take a shortcut by just setting the numerator equal to each of the numerators multiplied by what they don't have in the denominator in order to get that common denominator, right? So in this case, we have 4 is equal to a times the other two denominators, and that's what we have down here, a times x plus 1 times x minus 1, and then we would have plus b times the other two denominators, which is what we have right here, b times x minus 1 times x, and then we add that to c times the two denominators that it does not have, and so we have c times x plus 1 times x. All right, so that's the shortcut that we're going to use for future examples, but I wanted you to see how we get here without the shortcut first so that you understand what we are doing before we start skipping some of those steps that are a little bit unnecessary and time-consuming. Okay, and so if I clean up my work here, in order to solve for a, b, and c in this equation, what we're going to do is we're going to pick convenient values of x to plug into this equation that will then allow us to solve for one of these values at a time. So what I mean is that if you look at these factors, we have x plus 1, x minus 1, and just x. If we chose x to be 1, each of these x minus 1 factors would become 0, right? So if we let x equal 1, this term would become 0 because 1 minus 1 is 0, so you'd be multiplying 0 by this whole term. So this becomes 0, and this term would also become 0 because 1 minus 1 is 0, and so anything times 0 is 0, and so that whole term becomes 0, which just leaves us with c times 1 plus 1 times 1. Okay, so if we plug x equals 1 into this equation, we will have 4 is equal to 0 plus 0 plus c times 1 plus 1 times 1. Okay, so these two terms became 0, which eliminated b and a from the equation and just leaves us with c, and so we can solve for it. And so 4 is equal to c times 2, right? 1 plus 1 is 2, times 1 is still 2, and so if we divide both sides of this equation by 2, we will find that c is equal to 2. All right, so we found c. Now let's work on finding our other two values. If we plug in -1, then this x plus 1 quantity will become 0. That will eliminate this term with a, and it will also eliminate this term with c because -1 plus 1 is also 0 right here, and so this would become 0. And so if x is equal to -1, then our equation will become 4 is equal to 0 plus b times -1 minus 1 times -1 plus 0. So when x is equal to -1, this whole term becomes 0, and this whole term becomes 0, and so c and a are eliminated, and it leaves us with just b. And so now we can solve for b. And so we'll have 4 is equal to b times -1 minus 1, that is -2, times -1 is +2, and so we have b times 2, and once again, if we divide both sides by 2, we can solve for b, and we'll find that b is equal to 2. All right, and so that's what b is equal to. Now we just need to find a. And if we pick one more convenient value of x, we can find a. Note that this term with b and this term with c both have x by itself. If we just let x equal 0, then both of these terms will become 0. And so if x is equal to 0, then our equation will be 4 is equal to a times 0 plus 1 times 0 minus 1, and then the other two terms just become 0, and so we don't need to worry about those other terms. And so now we can solve for a. We'll have that 4 is equal to a times 1 times -1, and so that will become 4 is equal to -a, and if we divide both sides by -1, we will find that a is equal to -4. Okay, and so now with that, we have now found the values of a, b, and c, and so we can substitute those values in for our partial fractions. Let's start with a. We'll replace a with -4, then we can replace b with 2, and we can replace c with 2 as well. Those are the values that we found for each of those letters. And so now if I clean up my work, we have now successfully decomposed this rational function into 3 partial fractions. And so now we can go back to solving our integral by replacing that rational function with those 3 fractions. And so this will be equal to the integral of -4 divided by x plus 2 divided by x plus 1 plus 2 divided by x minus 1 times dx. Okay, and so now we can split this up into 3 separate integrals, one for each of these terms, and then work on solving each of those integrals individually. And so if we do that, we'll have that this is equal to the integral of -4 divided by x times dx plus the integral of 2 divided by x plus 1 times dx plus the integral of 2 divided by x minus 1 times dx. Okay, and so now if I clean up my work again, we can now integrate each of these integrals individually and find the solution to our original integral. Now what you're going to notice that when you're working with partial fractions and all of the factors in the denominator were linear factors, your solution to your integral is going to involve a lot of natural logs. And that is because these integrals that we're left with are easily integrated with the log rule of integration, right? Remember that the integral of 1 divided by x dx is equal to the natural log of the absolute value of x plus c, or the u substitution version of that is that the integral of 1 divided by u du is equal to the natural log of the absolute value of u plus c, where u is a function of x. Now this integral rule applies to all 3 of these integrals, which makes for an easy integration process. And so let me show you what I mean. For this first integral here, if we pull -4 out to the front, we would have that this is equal to -4 times the integral of 1 divided by x dx, and we know that the integral of 1 divided by x dx is the natural log of the absolute value of x. And so we can rewrite that and just have the natural log of the absolute value of x. Now for these other 2 integrals, we would normally use u substitution in order to solve them, right? Because the denominator is a function other than just x. However, in this case, both of these denominators, if you set them equal to u, their derivative is just 1. And so because of that, using u substitution is almost not necessary. And so I'm going to show you this process once, and then from here on out for the rest of the video, I'm going to skip the u substitution step when we have simple rational functions in our integral like we have for these 2, right? So if we're solving this integral here, if we set u equal to x plus 1, then du dx is equal to 1, because the derivative of x is 1 and the derivative of 1 is 0, which means that du is just equal to dx if we multiply both sides by dx. And so if we rewrote this integral in terms of u, we would have plus the integral of 2 divided by u times du. And so if we pulled that 2 out front, we'd have 1 divided by u du, which we know is the natural log of the absolute value of u. And so this integral would just become 2 times the natural log of the absolute value of u, and then we would replace u with what we set it equal to, which is x plus 1. And so we will have the absolute value of x plus 1. Okay, and so because the derivative of that denominator was just 1, which means that du is just equal to dx, this was a pretty simple integral to integrate. We just have 2 times the natural log of the absolute value of that denominator. And so when you see that the denominator is a simple linear factor like that, whose derivative is 1, you can skip this u substitution process and just integrate very quickly. And so that's what I'm going to do for this last integral. The integral of 2 divided by x minus 1 is just going to be 2 times the natural log of the absolute value of x minus 1 plus c. Okay, so it's just the constant in the numerator times the natural log of the absolute value of the denominator function. And that shortcut will work for linear factors where the derivative is just 1. Okay, so that's something to keep in mind because you're going to come across a lot of these integrals when you use partial fractions to solve rational functions. But with that, this is the final solution to our integral by using partial fractions. Let's look at another example. All right, so here's our next example. We have the integral of 3x minus 4 divided by x squared minus 4x plus 4 times dx. Now this is another integral of a rational function where in its current state, we cannot integrate it. And so we need to break it up into partial fractions. And the first step to doing that is to factor the denominator of that rational function. And so if we do that in this case, we have a quadratic in the denominator here that we can factor. And a quick trick to factoring a quadratic like this quickly, where the coefficient of the x squared term is 1, is we can ask ourselves, what two factors of 4, the last term, added together equal the coefficient of the middle term? Well, you could get 4 by multiplying negative 2 by itself, and negative 2 plus negative 2 would be negative 4. And so we can factor that denominator to be the following. This will be equal to the integral of 3x minus 4 divided by x minus 2 times x minus 2. Right? Negative 2 times itself is positive 4, and negative 2 plus negative 2 is negative 4. All right? And then don't forget your dx. But then notice that in the denominator, we have this same factor twice. We have 2 of these linear factors of x minus 2. And so if we combine them, this will be equal to the integral of 3x minus 4 divided by x minus 2 squared times dx. Okay, so whenever you have a repeated factor, or a factor that shows up more than once in the denominator, you should always combine them like so. All right, and so now that we have fully factored that denominator, let's take a little side trip and work on rewriting this rational function into partial fractions. And so we'll have 3x minus 4 divided by x minus 2 squared is equal to 2 partial fractions. Here's how they're going to look when you have a denominator of a repeated linear factor. You're going to have a constant a divided by that linear factor to the first power, and then you're going to add that to another fraction where we have a constant of b divided by that linear factor to the second power. Okay, so when you have a repeated factor, you're going to have a partial fraction for each one of those powers. In this case, we had 2 powers, so we have a fraction with that factor to the power of 1, and then we have a fraction with that factor to the power of 2. And so if this was x minus 2 cubed, we would have a third fraction, and we'd have c divided by x minus 2 cubed. But in this case, it's just squared, so we only need 2 fractions. Okay? So now let's set up an equation that will allow us to solve for a and b. We will take the numerator of this side of the equation, so we'll have 3x minus 4, and set that equal to a plus b, where each of them are multiplied by what they are missing in their denominator to have this common denominator. Okay? So let's start with a. We're going to have a times another factor of x minus 2. Right? The denominator here is x minus 2, but to get that common denominator of x minus 2 squared, we will have to multiply by another factor of x minus 2. So we have a times x minus 2, and we will add that to b, but we don't need to multiply b by anything because this fraction already has the common denominator, x minus 2 squared. All right, so this is the equation we will work with to solve for a and b. Let's start picking some convenient values of x. Notice that we have this factor of x minus 2. If we let x equal 2, then that will make this factor become 0, because 2 minus 2 is 0, and 0 times a will be 0. So our equation will look like this. We'll have 3 times 2 minus 4 is equal to 0 plus b. And so if we simplify, 3 times 2 is 6, minus 4 is 2, and so we'll have 2 is equal to b, and so that is the value of b. b is equal to 2. Now, in order to solve for a, we don't really have to pick a convenient value of x per se, because we already know what b is equal to, so we can plug in any value of x, and then plug in our value of b, and then we'll be able to solve for a. And so I'm just going to pick a simple value of x. I'm going to let x equal 0, and so if we do that, we'll have 3 times 0 minus 4 is equal to a times 0 minus 2 plus b, which we know is 2. Okay, so I just plug 0 in for each x in this equation, and then replaced b with what it's equal to, which is 2. And so if we simplify, 3 times 0 is 0, so we just have negative 4 is equal to a times 0 minus 2, so we have a times negative 2 plus 2. And if we subtract 2 from both sides of the equation, we will have negative 6 is equal to a times negative 2, and if we divide both sides by negative 2, that will give us that 3 is equal to a. Okay, and so we found the value of a and the value for b, and so now we can substitute them in to our partial fractions. So a is equal to 3, so we'll rewrite a with 3, and b is equal to 2, so we'll have 2 in that numerator. All right, and so now if I clean up my work, we can rewrite this rational function in our integral with these two partial fractions that we can then integrate. And so this will be equal to the integral of 3 divided by x minus 2 plus 2 divided by x minus 2 squared times dx. Okay? And then we can split this up into two integrals, one for each of these fractions. So this will be equal to the integral of 3 divided by x minus 2 times dx plus the integral of 2 divided by x minus 2 squared times dx. Okay? And so if I clean up my work again, we can integrate each of these integrals individually. This first one is just going to require the use of the log rule of integration. And so this is equal to 3 times the natural log of the absolute value of that denominator x minus 2, right? That is a linear factor where x is to the power of 1 and the coefficient of x is 1, and so the derivative of that factor is just 1. So we can skip that use substitution work and just write that this integral is 3 times the natural log of the absolute value of x minus 2. Now for this integral, it's going to be a little bit different. We can't use the log rule of integration here because we have x minus 2 squared, but we can use the power rule of integration with u substitution. So if we set u equal to that factor of x minus 2, then du dx is equal to 1 because the derivative of x is 1 and the derivative of negative 2 is 0. So du is equal to dx. And so if we rewrite this integral in terms of u, we will have plus the integral of 2 divided by u squared times du. And now we can move u squared to the numerator by making that exponent negative. And so if I rewrite this, we will have 2 times u to the negative second power, which we can then integrate using the power rule of integration. So this is equal to 3 times the natural log of x minus 2 plus 2 times u to the negative first power divided by negative 1, and then plus c. Okay, so we added 1 to the exponent to get negative 1, and then we divided by that new exponent. Now if I clean up my work again, we can simplify this. We can pull this negative to the outside, and then move u to the negative first power back to the denominator so that it is a positive power of 1. So this will be equal to 3 times the natural log of x minus 2 minus 2 divided by u plus c. Okay, so that negative came out, and we moved u to the negative first power to the denominator. So now all we have to do to finish this solution is replace u with what we set it equal to, which is x minus 2. So if we rewrite u, we'll have 2 divided by x minus 2, and this is the full solution to this integral by using partial fractions. Let's look at another example. All right, so here's our next example. We have the integral of 4x squared divided by x cubed plus x squared plus x plus 1 times dx. Okay, so just like with our previous examples, this is an integral of a rational function that we cannot integrate without decomposing it into partial fractions. Okay, so the first thing that we want to do is completely factor this denominator. Now initially, this denominator looks pretty complex, and you might not be sure how you can even factor it, but this is where your algebra skills are going to come into play. Remember that if you have 4 different terms, that you can try to factor by grouping. And so what I mean is that you will try to factor something out of the first 2 terms and then try to factor something out of the last 2 terms and see if you can find a common factor from what's left. And so let me show you what I mean. If you're not familiar with factor by grouping, this is going to be equal to the integral of 4x squared divided by this denominator. Now in the first 2 terms, we have a common factor of x squared. So if we pull that out of both of the terms, we will have x squared times x plus 1, right? X squared pulled out of x cubed leaves us with just x, and pulling x squared out of itself leaves you with 1. And then for our last 2 terms, we already have x plus 1. They really don't have a common factor other than 1. So if we pull out positive 1, it's not going to change anything, but we can write it like this, plus 1 times x plus 1. And now notice what we have in the denominator. we have a factor of x plus 1 in each of these terms that we can factor out, right? So this will be equal to the integral of 4x squared divided by x plus 1 times x squared plus 1, and that's still multiplied by dx. Okay, so all I did here was I pulled this common factor of x plus 1 out of each of these terms to the outside, and so we have x plus 1 times what's left over, which is x squared and 1. So we have x squared plus 1. That is how you factor by grouping. And so now what we're left with here is a linear factor and a quadratic factor. Now typically when you have a quadratic factor, I would try to factor it further, but in this case we're not going to be able to do that. We have x squared plus 1, which cannot be factored. If it was x squared minus 1, then we could factor it because we'd have a difference of squares, but in this case it's x squared plus 1, and so it just has to stay as x squared plus 1. And so now that we have completely factored the denominator, we want to work on breaking this down into partial fractions. And so we're going to do a little side work again. We'll have 4x squared divided by x plus 1 times x squared plus 1. And this is going to be equal to two partial fractions, one for the linear factor and one for the quadratic factor. So the linear factor is pretty easy. We're just going to have a divided by x plus 1. But then for the quadratic factor, that denominator will be x squared plus 1, but the numerator is not just going to be b. When you have a quadratic factor, meaning you have x to a second power, your numerator will not just be a constant. Your numerator will need to be linear. And so instead of just having b, we will have b times x plus c. Okay, so whenever you have a quadratic factor, you need to have a linear expression in the numerator of this form. It doesn't matter what letters you use, but you need to have some letter times x plus another letter. All right, and so these are the two partial fractions that we are going to work with to rewrite this rational function. And so if I clean up my work here, let's set up our equation to solve for a, b, and c. We will have this numerator on this side of the equation, and we will set that equal to each of these numerators multiplied by what they do not have in their denominator to have a common denominator. And so we'll start with a. It has x plus 1 in the denominator, but to have this common denominator, it also needs x squared plus 1. So we will multiply by x squared plus 1. Then we'll add that to b times x plus c, and this fraction does not have x plus 1 in the denominator, and so that's what we will multiply those two terms by. We'll have x plus 1. Okay? And so this is the equation we will use to solve for a, b, and c. Now in this case, the process is going to be a little bit different. The moment that you have a quadratic factor, I don't recommend that you try to plug in convenient values of x. Instead, what you want to do is expand everything on this side of the equation, and then there's going to be an easier way to solve for the values of a, b, and c that I will show you. But let's start by just expanding everything by multiplying a through this quantity and foiling these two quantities. So we're going to have 4x squared is equal to a times x squared. So we will have ax squared plus a times 1, which is just a. So we have plus a. Then we will add that to these two factors multiplied together. So we have to take turns with each of these terms and multiply them to each of these terms. So we'll start with b times x. We'll multiply that by x. And so we'll have b times x squared. Then we'll multiply bx by 1. And so we'll have plus bx. And then we'll multiply c by x. So we'll have plus cx. And then we'll multiply c by 1. And that's just going to be plus c. Okay? And so now that we have expanded everything over here, what we want to do is reorder our terms from the highest power of x to the lowest power of x. And so in this case, that would be from our x squared terms to our constant terms. So if we do that, we're going to have 4x squared is equal to all of our x squared terms, which we have two of them, ax squared and bx squared. And so I'll write those down, ax squared plus bx squared. Now, just so I don't forget any of our terms, I'm going to cross these out as I use them. Now we want to have all of our terms where x is to the first power. So I see we have bx and cx, and so we'll have plus bx plus cx. And we'll cross those out. And then we want all of our constants at the end, and so we have a and c, so we'll add a and c. Okay? And then I'll cross those out. And so now the reason we did that is now we are going to group the coefficients for each of those different powers of x. And so here's what I mean. We're going to pull x squared out of both of these terms. And if we do that, we will have 4x squared is equal to a plus b times x squared, right? We can multiply x squared back through and have both of these terms, but now we just have both of those coefficients times x squared. And then we'll do the same thing for bx and cx. We will have plus b plus c times x. I just pulled x out of both of those terms. And then our last two terms, we just have plus a plus c. Those are our two constants. All right, so now what we're going to do to solve for a, b, and c is set those coefficients equal to their corresponding coefficients on the other side of the equation. Now that might seem a little confusing because in this case we just have 4x squared, but I could rewrite that to be the following. We could have 4x squared plus 0 times x plus 0, right? Even though we just had 4x squared, we could also have a constant of 0 and an x to the first power with a coefficient of 0 as well. Both of them would just be 0, which is why we only write 4x squared, but now we can set each of these coefficients equal to the coefficients on this side for each of those powers, right? If this side of the equation is equal to this side of the equation, then the coefficients for each power should be equal. So we'll set 4 equal to a plus b for our x squared terms. So I'll write that down. 4 is equal to a plus b. Then we'll set 0 equal to b plus c for x to the first power. So we'll have 0 is equal to b plus c. And then we'll have 0 is equal to our constants a plus c. So we have 0 is equal to a plus c. All right, and so now if I clean up my work, we now have a system of 3 equations that we can use to solve for a, b, and c. All right, so this might seem a little complicated at first, but notice that all 3 of those letters appear in 2 of these equations, and so we're going to be able to substitute things in to solve for our values. So to start, let's work with this bottom equation. If we subtract c from both sides of the equation, we will find that negative c is equal to a, and if we do the same thing for this equation, if we subtract c from both sides, we will find that negative c is equal to b. And so since both a and b are equal to negative c, we can conclude that a is equal to b, right? We could replace negative c with a in this equation, and a is equal to b. They're both equal to negative c, so they must be the same. And so if we use that knowledge for this first equation, we know that 4 is equal to a plus b, and if they're just the same thing, then that means that 4 is equal to a plus a, right? We can replace b with a since they're equal. And so 4 is equal to 2a because a plus itself is 2a. And then if we divide both sides by 2, we will find that a is equal to 2. And so that's one of our values. And now we can get the other 2 pretty quickly, right? We know that a is equal to b, so that means that b is also equal to 2, right? If a is equal to 2 and a equals b, well then b equals 2 as well. And then if we use these 2 equations, we know that a is equal to negative c and b is equal to negative c. Well, that just means that c is the negative version of a and b. And a and b are both 2, and so that means that c must be equal to negative 2. Okay? And so those are our 3 values. And if you weren't quite following that last bit where I got c, you could just plug a equals 2 into this equation. Right, we said that negative c is equal to a, and if a is equal to 2, then negative c is equal to 2, and if you divide both sides by negative 1, that will give you that c is equal to negative 2. Just in case my logic before didn't make sense to you, but either way, we found all 3 of our values, and so we can substitute them in to our partial fractions. So a is equal to 2, so I'll rewrite that with 2. B is equal to 2, so I'll rewrite that with 2 as well. We'll have 2. And c is equal to negative 2, so this plus c will become minus 2. Okay, and so now if I clean up my work, we can now rewrite this rational function that's in our integral with these 2 partial fractions. And so we'll have that this is equal to the integral of 2 divided by x plus 1 plus 2x minus 2 divided by x squared plus 1 times dx. Okay, and so now if we split this up into 2 separate integrals, this is equal to the integral of 2 divided by x plus 1 times dx plus the integral of 2x minus 2 divided by x squared plus 1 times dx. Okay? And so now if I clean up my work, we can now work on integrating each of these integrals individually. And so we can actually integrate the first one by using the log rule of integration, right? We just have a constant divided by a linear factor whose derivative is just 1. And so let's do that right away. This is just going to be equal to 2 times the natural log of the absolute value of x plus 1. Now for this integral, it's going to be a little bit trickier. It's not initially clear how we can integrate it. However, we could split this up into two integrals by splitting the numerator and dividing each part by that denominator. And so watch what happens if I do that. We'll have plus the integral of 2x divided by x squared plus 1 minus 2 divided by x squared plus 1 times dx. Okay, so we just split up that numerator and we have each part divided by that denominator. Now what we have is two more fractions that we can integrate individually. So if I rewrite that, this is equal to 2 times the natural log of the absolute value of x plus 1 plus the integral of 2x divided by x squared plus 1 times dx minus the integral of 2 divided by x squared plus 1 times dx. Now if I clean up my work again, this integral here we can solve with u substitution, because if we set u equal to the denominator, x squared plus 1, its derivative is in the numerator. The derivative of x squared plus 1 is 2x. And so that's going to work. And then for this integral, we can actually use another special integration rule like the log rule of integration. Except it's not the log rule, it's going to be a rule for one of our inverse trig functions, right? If I pull this 2 to the front, so if I rewrite this to be 1 divided by x squared plus 1, and then have negative 2 out front, this integral right here, the integral of 1 divided by x squared plus 1 times dx, is one of our special integration rules, and it is equal to arc tangent of x, the inverse tangent function. And of course, you could add plus c to that. That would be the correct solution to this integral. But either way, that is the solution to this integral. So we'll have negative 2 times arc tangent of x plus c. Okay, and so now we know how we're going to integrate our last two integrals. And so let's do that. Let's start our u substitution process on this integral here. We will let u equal x squared plus 1, which means that du dx is equal to 2x, right? We multiply that exponent down, so we have 2 times x to the power of 1 because we subtract 1 from that exponent. And then, of course, the derivative of 1 is just 0 since 1 is a constant. Then if we multiply both sides by dx, we will have that du is equal to 2x dx, which we can find in our integral and replace with du. And so we'll have that this is equal to 2 times the natural log of the absolute value of x plus 1, and then we can rewrite this integral in terms of u to have plus the integral of 1 divided by u times du, and then if we integrate this integral, we'll have minus 2 times arc tangent of x plus c. All right, and now we know that the integral of 1 divided by u is just the natural log of the absolute value of u, and so this will be equal to 2 times the natural log of the absolute value of x plus 1 plus the natural log of the absolute value of u minus 2 times arc tangent of x plus c. And now all we have to do to finalize our answer is replace u with what we set it equal to, which is x squared plus 1. And so if I rewrite this, we'll have the natural log of the absolute value of x squared plus 1. And then if you wanted to, since x squared will always output a positive value and you're adding 1 to it, we don't even need these absolute value bars. We could just have the natural log of x squared plus 1. Okay, and so that is the final answer to this integral by using partial fractions. Let's look at one more example for this video. All right, so here's our last example. We have the integral of x to the 4th power minus 3x squared minus 3x minus 2 divided by x cubed minus x squared minus 2x times dx. All right, so this is going to be a little bit different than our previous examples. I didn't make an explicit note of it, but all of the previous rational functions that we have been integrating by first decomposing them into partial fractions, they were all rational functions where the polynomial in the numerator was of a lower degree than the denominator. And so what I mean by that is the highest power of x in the numerator was less than the highest power in the denominator. Now in this case, we have x to the 4th power, which is greater than the highest power down here, which is x to the third power. And so when you have a rational function like this, and there's clearly no other way to integrate it, you still want to use partial fractions in order to solve it, but you're not going to be able to do it right away. You can only use partial fraction decomposition when the degree of the polynomial is less in the numerator than in the denominator. And so in order to get this rational function into that form, what we need to do is divide this polynomial by this polynomial. And so what that means is we are going to have to use long division for polynomials. And so this is something that you cover in algebra, but if you don't quite remember, don't worry, we're going to go over it here. We're going to start by writing our divisor. So we'll have x cubed minus x squared minus 2x, and then we're going to divide that into the numerator. And so we want to write all of these terms, but we want to make sure to fill in any missing places. And what I mean by that is note that we have x to the fourth power and then x to the second power. We completely skipped x to the third power, and so we don't want to skip that when we write out our terms. So what we'll have is x to the fourth power plus 0 times x to the third power, and then we'll write the rest of our terms and have minus 3x squared minus 3x minus 2. Okay, and so the reason we do that is so that we can line up all of our terms when we do the long division process and subtract everything from the right term. And you'll see what I mean if you're not quite familiar with long division. Okay, so what we're going to do is we're going to divide this polynomial into this polynomial. And the way we do that is we look at the first term of our divisor and ask ourselves, what can we multiply by that term to get the first term of what we're dividing into? And so to get x cubed to become x to the fourth, we just have to multiply it by x. So we'll write down x, and then we will multiply x by each of these terms. So x times x cubed is x to the fourth, then x times negative x squared is negative x cubed, then x times negative 2x is negative 2x squared. And then what we will do is we are going to subtract these terms from this polynomial. So we're going to negate each of these terms and add them to the term above them. So this will be negative x to the fourth power plus x cubed plus 2x squared. And so if we combine those terms, x to the fourth minus x to the fourth is 0. 0x to the third plus x to the third will be positive x to the third power. Negative 3x squared plus 2x squared will be negative x squared. And then we just bring these other two terms back down. So we have negative 3x minus 2. All right, and so then we do the whole process again, but instead of looking at these terms, we're going to look at these terms. So what can we multiply by x cubed to get x cubed? Well, we just multiply it by 1, so we'll add 1 and multiply 1 by each of these terms. So we'll have x cubed minus x squared minus 2x. Now if we subtract those terms, we'll have negative x cubed and then plus x squared and then plus 2x. And so if we combine all of those terms, x cubed minus x cubed is 0. Negative x squared plus x squared is also 0. And then negative 3x plus 2x is negative x. And then we just bring down this negative 2. Now at this point, we are done because we can't divide a third degree polynomial into a first degree polynomial. And so we are done with the long division process. We can now rewrite this rational function with the results from this long division. And here's what it looks like. We start with our quotient of x plus 1. So this integral will be equal to the integral of x plus 1. And then we will add our remainder, negative x minus 2, divided by our divisor. So we will have negative x minus 2 divided by x cubed minus x squared minus 2x. And all of that is multiplied by dx. Okay, and so now we have successfully divided this fourth degree polynomial by this third degree polynomial to get these terms. And so now we can simplify a little bit. I'm going to pull a negative 1 out of each of these terms. And so if I do that, negative x minus 2 is going to become negative 1 times x plus 2, right? If we multiply that negative 1 back through, we'll have negative x minus 2, which is what we had before. And then I'm going to bring that negative 1 out front, and so then we'll just be subtracting this part of our function. So we'll have minus this rational function. Okay, so we no longer need this long division work. We can now work on further simplifying our integrand. Now these two terms right here are pretty easy to integrate, and so let's just do that real quick. this will be equal to the integral of x, which if we use the power rule of integration, we add 1 to the exponent and divide by the new exponent. So we have x squared divided by 2, and the integral of 1 is just x. So we'll have plus x, and then we will subtract the integral of this rational function. So we'll have x plus 2 divided by x cubed minus x squared minus 2x dx. All right, and so now this rational function here can now be decomposed using partial fractions. We now have a first degree polynomial divided by a third degree polynomial, and so the degree in the numerator is less than the degree in the denominator. Okay, and so now if I clean up my work, let's factor this denominator here. I see that each of these terms has a common factor of x, and so if I pull that x out, this will be equal to x squared divided by 2 plus x minus the integral of x plus 2 divided by x times x squared minus x minus 2 times dx. Okay? And so x is going to be one of our factors, but then we have this quadratic here that we can factor further. So since we have x squared with a coefficient of 1, we can ask ourselves what factors of negative 2 added together will give us the coefficient of this term, which is negative 1. And in this case, negative 2 times positive 1 is negative 2, and negative 2 plus positive 1 is negative 1. And so this will be equal to x squared divided by 2 plus x minus the integral of x plus 2 divided by x times x minus 2 times x plus 1. All right, so that is the factorization of this quadratic. Negative 2 times 1 is negative 2, and negative 2 plus 1 is negative 1. Okay, and so now we can work on decomposing this rational function. So we'll do a little side work. X plus 2 divided by x times x minus 2 times x plus 1 will be equal to 3 partial fractions, 1 for each of these 3 linear factors. And so since they're all linear, this is pretty easy to set up. We're just going to have a divided by the first factor, x, plus b divided by the next factor, x minus 2, and then we will add that to c divided by the next factor, which is x plus 1. Okay? So now we can set the numerator equal to each of these letters times the factor that they don't have in their denominator that would give them the common denominator. So we're going to have x plus 2 is equal to a, and a has a denominator of x, but it needs x minus 2 and x plus 1 to get the common denominator. So we'll have a times x minus 2 times x plus 1, and then we'll add that to b, and b has a denominator of x minus 2, and so it needs x and x plus 1. So we'll multiply that by x plus 1 and x, and then we'll add that to c, which has a denominator of x plus 1, and so it needs x minus 2 and x. And so we'll multiply by x minus 2 and x. Okay? And so now we have an equation here that we can use to solve for a, b, and c. Now if I clean up my work a little bit, since we're working with all linear factors, we can go back to our original method of just picking convenient values of x to plug into our equation to be able to solve for a, b, and c. And so let's start with plugging in 2 for x, because I see we have a factor here of x minus 2. So if I make x equal to 2, then this whole term will become 0. So if x is equal to 2, we will have 2 plus 2 is equal to 0 for this term, and then plus b times 2 plus 1 times 2, and then plus 0 because this term also has x minus 2, and so 2 minus 2 is 0, and so this whole term will become 0. Now if we simplify, we'll have 4 is equal to b times 3 times 2, and so 3 times 2 is 6, so 4 is equal to 6b, and if we divide both sides by 6, then we'll find that b is equal to 4/6, which reduces to 2/3, and so b is equal to 2/3. Okay, so we found b. Now let's work on another letter. If we plug in -1 into this equation, that will make these two terms 0 and allow us to solve for c, because if you plug in -1 for x, x plus 1 will become 0, and the same will occur over here, so both of these terms will be 0. So if x is equal to -1, we will have -1 plus 2 is equal to 0 plus 0 plus c times -1 minus 2 times negative 1. And so if we simplify, we'll have positive 1 is equal to c times negative 3 times negative 1. And negative 3 times negative 1 is positive 3, so 1 is equal to 3c, which means that c is equal to 1/3 if we divide both sides by 3. And so c is equal to 1/3. Now I'm running out of space to solve for a, and so let's just replace c and b in our partial fractions with their values, and then we'll work on solving for a. So we know that b is 2/3, so I'll erase b here, and we'll switch that out, and we'll replace that with 2/3. And then c is equal to 1/3, so I'll replace c with 1/3. So I have 1/3. Okay, now if I clean up my work, let's plug in another convenient value of x to solve for a. And now in order to do that, I see that our terms with b and c both have just x in them. And so if we let x equal 0, both of these terms will become 0. And so if x is equal to 0, we will have 0 plus 2 is equal to a times 0 minus 2 times 0 plus 1 plus 0 plus 0. Okay, so both of these terms become zeros, and now we can solve for a. And so 2 is equal to a times negative 2 times positive 1, and so 2 is equal to negative 2a, and if we divide both sides by negative 2, we will find that a is equal to negative 1. And so that's the value of a, and so let's substitute that in for our partial fractions. So a will become negative 1. Okay, and so now if I clean up my work again, we now have our three partial fractions that we can use to rewrite this rational function and then integrate it. So this will be equal to x squared divided by 2 plus x minus the integral of negative 1 divided by x plus 2/3 divided by x minus 2 plus 1/3 divided by x plus 1 times dx. All right, now if we split this up into three separate integrals, we'll have that this is equal to x squared divided by 2 plus x minus the integral of negative 1 divided by x dx plus the integral of 2/3 divided by x minus 2 dx plus the integral of 1/3 divided by x plus 1 times dx. Okay, now if I clean up my work, let's distribute this negative to each one of these integrals. So this will be equal to x squared divided by 2 plus x minus this integral, but those two negatives will cancel out. So we will have plus the integral of 1 divided by x times dx. And then we will have minus the integral of 2/3 divided by x minus 2 times dx. And then we will subtract the integral of 1/3 divided by x plus 1 times dx. Okay, and now we have three integrals that can easily be solved by using the log rule of integration. Right, we can pull these constants to the outside of the integral, and if we did that, we'd have 2/3 times this integral, and we just have 1 in the numerator. And then if we pulled 1/3 out, we would have negative 1/3 out front and 1 in the numerator. And then hopefully now you can see a little bit better how we're going to use that log rule of integration. Since their denominators are all linear factors where the derivative is 1, we can just integrate right into that natural log function without using u substitution. So we'll have that this is equal to x squared divided by 2 plus x plus the integral of 1 divided by x, which will be the natural log of the absolute value of x, minus 2/3 times the integral of 1 divided by x minus 2, which will be the natural log of the absolute value of x minus 2. And then we will subtract 1/3 times this integral of 1 divided by x plus 1, which will be the natural log of the absolute value of x plus 1. And then don't forget to add plus c. And that is the final answer to our original integral using partial fractions. Okay, and so with that, this was the last example for this video. And so if you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.